Okay, so welcome to part one of a three-part series of learning about adiabatic reversibility expansion problems for an ideal gas. But before we do that, so part one of this is going to be the basic equation of statics, or the basic statics equation. Um, so here we have a volume of liquid. So yeah, we have a volume of liquid that of height dz, and then this a right here is the area. Um, so what we have to do, so to start off, we're going to apply the regular force equation. So F is equal to mass times acceleration. And for here, so we can go ahead and assume that this differential volume of liquid is not moving. So our acceleration is actually going to be equal to zero. So that means our net force is also going to be equal to zero. But before we do that, we have to figure out what forces are actually acting upon this object. So to start off, let's say we have a point right here at height z, or quote unquote height. So the force at this point z is going to be equal to the pressure times the height, which at that point is z. And that's going to be positive because, as we can see right here, we're just denoting that the upwards direction is the upwards direction is positive for us. So we have one force going up, so that's the pressure at z times times the area. So that is the force going up. We also have another force going down, which is the area times the pressure of point z plus this height right here, which is dz. So we can say z plus dz, or we can just, instead, so we don't have to write that every single time, we can just say that is area times p, and then we can just call it d or something like that. And then we also have gravity acting upon the object as well. So we just have gravity there. So like I said, acceleration is going to be equal to zero just for simplicity of this problem. So that means our net force is equal to zero. So our net force is equal to zero. So that means that the sum of those three forces that we just wrote down has to also be equal to zero. So we can say that, so we have pz times a minus pd times a minus gravity times the mass of that whole thing. So then now what we can actually do is we're going to want to move this gravity times mass over to the other side. So we have gravity times mass is equal to pz times a minus pd times a. And then we can go ahead and factor out one of the a's at this point. So we can say gravity times mass is equal to the negative area. That'll be important later. So we can take out the negative area, so then we can flip it around, so we can make it pd minus pz. So then that should be a positive number if we're talking about it from the top to the bottom. So then now it looks like we can't really do much more with this, but we can actually denote the mass, because if we look, we can see that the mass is the density times the volume. That's the definition of mass. And then from there, so that we can put that in, but then we can also say that the volume is just this dz right here times the area. So the volume is just dz times a. So then we can go ahead and plug that back into the equation there and make this gravity times the gravity times the density times dz times a is equal to negative a pd minus pz. So then from there, we can see that we have A back in the equation, so we can go ahead and cancel that out, and just so we can get rid of the negative on the one side, we can have this equal to, we can just divide by the negative A. So then we can make this negative G rho dz is equal to PD over PZ. And then from there, so this, the PD minus PZ, we can just denote that as the change in pressure, because this length right here, the dz that I have now scribbled all over, is essentially what we're saying, the change in height, or the change in height of that volume of liquid. So we can make that, we can take this dz and put it on the other side. So if we make this PD minus PZ, if we just make that dP, or not dP, yeah, dP. So then we can get negative G rho is equal to dP over dz. But now, since we want this equation to be like a basic equation that is versatile for multiple liquids and everything like that, we can take the density, because the density varies for every liquid, but since we're working with an ideal gas, essentially, or an ideal fluid, so density is equal to mass over volume. But again, we don't want mass in there because we don't want it to vary. So we can also rewrite that as the number of moles times the molecular weight, so I'll make that a big M, over the volume. And if we recall to the ideal gas law, RT, that's an R, let me get rid of that. So PV is equal to nRT. We can substitute that in for that number of moles over the volume. So if we get that, we can do, we can move this P over, or no, move other way. Move this over, and then move the V over the N. Okay. So yeah, I was doing that wrong. So then to get N over V, so we move this RT over the other side. So PV over RT equals number of moles, and then just move the V over the other side. So just like that. So P over RT is equal to NV. So then we can go ahead and plug that back into the density equation. So then we can rewrite that as density is equal to PM over RT. So then this is, so dP over dz is equal to negative G times the pressure times the molecular weight over RT. And that is the basic cubic equation of state, not cubic. That is the basic equation of state for an ideal fluid with differential volume. And in part two, we'll look at the beginnings of adiabatic reversibility in a ideal gas that is increasing in volume with an increase in altitude.